Well, hello. Okay, this is the first tutorial of the Math1231 Calculus course. The main reason for conducting this tutorial electronically rather than manually is a persistent pain in my right hand, especially if it is doing something like writing on a board. It's actually better now, but however, some other staff have begun to present tutorials electronically, so I thought a different approach might enrich the debate. So let's go down a bit. Not that far. So this document is written using the notebook interface of the computer algebra system Mathematica. I apologise for not using the school system Maple, but I've been using Mathematica for teaching and research for some 15 years. And Mathematica allows the integration of text, which we're reading now, symbolic code fragments, which we'll see in a bit, and performing mathematical operations, mathematical equations, as well as graphics and animation. I can create the basic mathematical narrative in which I use Mathematica to solve the assigned problems on my laptop, which connected to a PC projector enables me to share my thoughts with you. However, I can use a screen capture program, in this case Camtasia, to store the dynamical screen picture and voice input in a video file. And this video file can then be edited and compressed into MP4 format and loaded up onto my YouTube channel, which is called John Perham, and where you can see you and the whole world can see it from tomorrow morning. So let's start the tutorial. So let's start with problem 1. And problem 1 says for each of the following surfaces, sketch some level curves and sketch the YZ profile, which is found by intersecting the surface with the plane x equals 0. Hence, sketch the surface. So, okay. So, we need to write down the equation of the surface. This is part C, by the way. We can write the left-hand side of the equation of the surface in this way. And this is a code fragment, and I can execute it like so. So note that the left-hand side of the equation is equal to 0, and I always use that convention. And this code fragment assigns the name surface to the formula on the right. So we can see that by executing this code fragment, surface, and the answer is this right-hand side here. So how do we get the solution to the problem? Well, the level curves of a surface are the intersections of the surface with planes z, little z, which is the variable, equal to big Z, which will be a number. So we can define this name L curve for level curve, and we can do that by taking the surface and replacing little z by big Z. So this form, or this symbol here, assigns that value big Z to the value of little z. So let's execute that. And we can see that the result has replaced the variable little z by big Z. If we look at this, or if we move the -1 and the z squared onto the other side of the equation, we can see that the equation of the level surface is the equation of a circle with radius the square root of 1 plus z squared. So we can get an equation for these curves can be found by setting them equal to 0 and solving for y as a function of x and z. And we can do that using this. Well, we better set the radius, otherwise it won't work. So we set the level curve equal to 0 and solve for y. And we get these two solutions here. And what we've done here is we've used the mathematical symbolic equation solver called solve, which takes an equation and tries to find the value of a variable for which the equation is satisfied. Okay, well, if we put this, hello, you can. So this is notice that this expression with the double zero here is yet another way that mathematicians use the concept of equality. And if you want to learn more about the different ways mathematicians use the concept of equality, you can look up one of my presentations called The Meanings of Equality, which is on my YouTube channel. So this gives me a parametric equation of part of the curve using this. So this is a vector, and it is a function, or each component is a function of x apart from the value of z, which is a constant. So that's a level curve. And we can do that for the second solution, like so. And now we can draw the level curve z equals 0. So we use this Mathematica function called parametric plot 3D, and we take the two parametric equations and we set the value of z equal to 0, and we plot that for x between minus the radius, setting z equals 0, and plus the radius. And we want to plot both curves in red and thick, and we want the axis labels to be x, y, and z. So let's do that. And lo and behold, well, we get this three-dimensional plot here. Now, we're prepared to believe that this is a circle, but if we look at it, it's actually an ellipse. Well, three-dimensional graphics objects are made to look three-dimensional using a thing called the perspective transformation. There are some videos on my channel called Understanding Perspective, which explains how this works mathematically. So I can now essentially copy that last command and change the value of z from 0 to 1 and plot that level curve using this. And that's another ellipse, or it's also a circle. And now I can superimpose those two curves on the same graph, because I called the first one graph 0 and the second one graph 1, and I can do that using that. And so you begin to see what they look like. And now I can now plot the level curve at z equals -1 by replacing, essentially copying the first graphics command and replacing z equals 0 by -1 and getting that in blue as well. And now I can superimpose the three graphs to give me that. So that gives some idea what the surface looks like. It's if you cut it in a horizontal plane, then the result is a surface. So now let's move on to the YZ profile. So the YZ profile is obtained by setting x equals 0 in the equation for the surface, and we can do that using this. And we can set that equal to 0 and solve for y as a function of z using this. So we take YZ profile, set it equal to 0, and solve for y using the Mathematica solve program. And this, so Mathematica finds two solutions, and we can obtain the parametric equations of the curves, and first curve and the second curve, and we can plot those in 3 dimensions using the same Mathematica graphics routine. Plot them in black, and that's what that graph looks like. And again, we can see it's a 3-dimensional object plotted using perspective. And now we can plot all the graphs together to see if we can work out what's going on. And I guess the answer is not very clearly, but anyway, we've done it. So how do we draw a graph of the surface? Well, we can take the equation of the surface and set it equal to 0 and solve for the value of the vertical coordinate z using that. And we get those two solutions here, and they're real for all points outside the unit circle. We can see that this equation here, if we set it equal to 0, is the equation of a unit circle. So we can try to plot the whole thing using this. So plot is a Mathematica command which plots a function of x and y, which is given by z, the second solution, and it looks like that. And we can see that Mathematica cleverly omits the central circular region where the value of z is imaginary. So the whole surface can now be plotted using that. So we take the first surface solution, the second solution, and plot that. Now this looks a bit different from our original representation. Oh, we can do another thing with all this. We can rotate it around so you can get some idea of what the surface looks like. But it looks a bit different from our original representation, and you can see the reason for this is that the scale on the vertical axis is different from the scale on the horizontal axis. So the whole surface has been compressed downwards. So we'd like it to be plotted with the same scale on each axis, and we can do that by transforming the equation to polar coordinates, or cylindrical polar coordinates. And we do that by replacing x in the equation of the surface by r cos theta and y by r sine theta. So this is the transformation from Cartesian to polar coordinates, and we do that. And now we can take the equation of the surface and replace x and y by these expressions involving r and theta using this relation here. And this looks a bit complicated, but we can simplify it using by doing this. So we take the Mathematica function simplify and apply that to the parametric surface. And of course, what this simplify function does is it's a mathematical function which attempts to use a lot of mathematical knowledge, in this case the theorem of Pythagoras, because this is actually equal to r squared, to simplify expressions. We can set the result equal to 0 and solve for z using this. And the parametric equation of the surface can then be established by taking x, y, and z and replacing x and y by their polar expressions and z by the first solution there. And so x becomes r cos theta, y is r sin theta, and z is just this expression of r, or this expression involving r. So we can solve this, find the second polar equation, or parametric equation, and now we can plot that, or these two things here, by choosing theta to lie between minus pi and pi, and r to lie between 1 and 3. So we can draw that. And now we see that the scales on the two axes are the same, and we can turn this around and look at it and so on. So that's what the surface looks like. So this surface is known as a hyperboloid of one sheet. So that was the solution of question 2. First question, problem 1. So let's move on to problem 3. So problem 3 is about partial derivatives. So we're given a number of functions, and for each of them we're asked to find all first and second order partial derivatives and verify that the mixed partial derivatives are equal independently of which order we do the differentiation. So we take this function part c, z is sine of x minus cy, and we establish that. And now we can find the partial derivative with respect to x using this function here. So d is the mathematical differentiation function, and it differentiates the quantity z we've defined up here with respect to x, partially. And you can see that that just gives the cosine of x minus cy. So the mathematical function d, expression variable, computes the partial derivative of the expression with respect to the variable. Thus, dz dy is equal to we apply the function d to z and with respect to the variable y, and we get that. So that's the first partial derivatives. So now let's get the second ones. So we want the d2z dx squared. So we do that, we take the expression for dz dx, which we found above, and we differentiate that with respect to x using this. And that gives me that expression here. And I can do the same thing with the partial derivative with respect to y to get d2z dy squared using that. And we can see that that is c squared times this guy here. Anyway, let's now define d2z dy dx, and we take d2z dx and we differentiate that with respect to y. And that gives me that. And now we do the same thing in the opposite order. So d2z dx dy is got by taking dz dy and differentiating with respect to x, and we can see that they're equal. So that was the second part of the problem. Now, all that remains to do is to deassign this function z, because we may want to use the variable z again as a coordinate, for example. So that's done by this function clear, which removes whatever definition we had from z. So here's problem 4. We have to find a normal vector n and the equation of the tangent plane to the surface at the point r0. I use the symbol r for the vector whose components are x, y, z. And we want to do this for part D. So part D, we have this surface here, x squared plus y squared plus z squared equals 1. And of course, that's just a unit sphere. So let's establish that surface. And the point at which we want to evaluate the tangent, or construct the tangent, we're given this point. It's a third, a half, and the square root of 23 divided by 6. So we execute that. So, the surface, as I said, was a sphere of radius 1 with center at the origin, and we can see this by setting the expression to 0 and solving for z using this. And of the two solutions, we can see the first is negative and the second is positive. So these two solutions give z for the lower and the upper hemisphere. And we can, the first part, we can get a parametric representation in cylindrical polar coordinates by replacing z by this solution here and using our previous expression for the transformation from Cartesian to polar coordinate. And you'll find this quite a lot if you start using something like Mathematica to solve these problems. You'll find that you can define tools like the transformation from Cartesian to polar, and you can reuse them again and again. So that's the expression for the first surface in polar coordinates, and we now take the second one and we can do that like so. So we can plot this, the whole surface, by taking these two parametric equations and plotting them for theta lying between minus pi and pi, and r going from 0 to 1.5, say. And so we do that. And there we have a picture of the sphere. So we can construct a tool for assigning the values of the coordinates at the vector r0 by defining this vector containing the variables x, y, and z, and building a table such that the value of each variable is set to the corresponding element in the vector of coordinates. And we do that for each of the or each of the three components of variables x, y, and z. So what does that give us? Well, that gives us this, which sets x to a third, y to a half, and z to this value here. Well, we better check that the point r0 is on the surface, and we do that by replacing the values of x, y, and z by these values here, and the result should be 0. And it is. So this point does lie on the surface. So how do we calculate the components of the normal? Well, we take the positive derivative of z, the first one. Well, we're in the, let's look at these coordinates here. We can see that the value of z is positive, so this means that we need the second solution for z, and so we take z and differentiate it partially with respect to x, and then the second component of the normal is the same thing, where we differentiate the expression for z, the positive expression, with respect to y, and then the third, according to the book anyway, the third coordinate is -1. And this is the expression for the normal to some point on the curve. And this can be evaluated at the given point by taking this expression n and replacing x, y, and z by the variables, or x and y, by the values. And that gives me that. So this is the equation of the normal to the surface. Well, having found that, any point on the tangent plane has to be perpendicular to this vector. So this leads us to calculate the left-hand side of the Cartesian equation of the tangent plane using this expression here. So the tangent plane, we take the vector connecting the variables to the point on the surface, and then we take the scalar product with the normal vector, and since this vector here has to be perpendicular to that, so that will give us the equation of the surface. And there it is. And we can set that equal to 0 and solve it for z using this. Now I've used this mathematical function flatten here, which removes excessive numbers of curly brackets here. Anyway, the parametric equation of the plane can then be obtained by taking the values of the variables and replacing them by the solution. The values of the variables, replacing them by the solution. And that's that. And now we can plot the equation of the plane by using again this function parametric plot 3D to we take the parametric equation of the plane and we plot it for x going from 0 to 2 and so on. And so we do that, and that's what it looks like. And now we can superimpose that on the graph of the surface, and we get something that looks like that. And now we have to check that that actually is the tangent plane. So let's just rotate the whole lot, and you can see that the plane does just touch the curve there. So there we are. So we have indeed found the tangent plane. Okay, so that's the solution to those equations. So let's